RoMo, Robust Motion Segmentation improves structure from motion. Structure from motion pipelines such as call map and on-post collection of images from a scene to their camera poses. These camera annotations are useful in applications such as 3D or 4D reconstruction and camera-controlled video generation. But does SFM work effectively on scenes with dynamic components? The answer is often no. Here we show a billiard scene with a few dynamic elements. When we tested this on call map, we see that the camera estimation fails. There are previous work like Particle SFM, LeapVO, and finally Monster that address the problem of SFM on videos with transient objects. Most of these methods try to learn priors to distinguish between static and moving objects and heavily rely on annotated synthetic data in their training. Although effective, they have trouble in generalizing to real scenes. This shows that although this is a very promising path to solve this problem, we need real annotated data with camera poses and motion masks for better performance. We first analyzed the classic process for two-view camera pose estimation. Given a video, we first establish dense correspondences between adjacent frames using off-the-shelf optical flow models. Next, we solve for the fundamental matrix F using a ransack solver on the epipolar constraint. This fundamental matrix lets us compute a per-pixel epipolar error. From this error map, we can draw an important insight. Highly dynamic regions tend to have large epipolar errors, while static regions show low errors. We can use this insight to obtain a coarse labeling of which parts of each frame are likely dynamic and which parts are likely static by simply thresholding the error. Next, we leverage the well-structured feature space from SAM-V2 and train a simple MLP classifier to distinguish between dynamic and static regions. The key idea is that the MLP learns a smooth decision function. Even though it's trained only on coarse labels, it maps nearby features to similar classes, producing a complete and coherent mask of the dynamic areas in the scene. This process can be iterated to progressively improve both the fundamental matrix and the resulting dynamic masks. After one iteration, we can filter out dynamic correspondences from the optical flow matches, then resolve the fundamental matrix using only the remaining and more reliable correspondences. This yields a better camera pose estimate, which in turn gives cleaner epipolar errors and thus improved coarse labels for the next round of MLP training. We see that repeating this procedure 2 to 3 iterations is usually enough for the process to stabilize. Here are some results for our motion segmentation on the same billiard scene. The pink masks show all the moving objects. By just providing classic SFM like call map with these masks, we avoid failure and arrive at a close estimation to ground truth cameras. Here are some more results on challenging motion segmentation benchmarks. We show performance on scenes with motion blur, scenes with occlusion on the moving object, scenes with multiple moving objects, and slow motion videos. We evaluate how our masks improve upon call map in camera pose estimation on the synthetic MPI Sintel dataset. We outperform all baselines. We further collect 8 real scenes with ground truth camera and motion mask annotations in a dataset called Casual Motion and evaluate our method, showing call map with our masks outperforms all the other previous methods. Finally, we demonstrate the application of our method to robust 3D reconstruction. In scenes with moving distractors such as pedestrians, methods like 3D Gaussian splatting often produce visual artifacts. By applying our dynamic masks, we can effectively filter out these distractors, achieving performance comparable to robust reconstruction approaches such as SLS. Thank you for listening.